gravitational potential. Now we will define gravitational potential at a point. Okay, the first thing. Definition. Now we'll just write the complete sentence and then we will make it short. Gravitational potential at a point is the work done in moving unit mass unit mass means 1 kilogram from infinity to that point without acceleration. So the complete definition is like this: the gravitational potential at a point is the work done in moving unit mass from infinity to that point without acceleration. Or you can simply say this. The easiest way to put it is like this. Is that what is it? Work done per unit mass to move from doesn't look nice. No, from infinity to a point. Now you must remember, when you work out the gravitational potential, we make an assumption, because gravitation, you must remember a couple of points. Let's write that points first. All right, let's put it in there. All right. The first point you must remember, potential. This is not just for gravitational potential. This is true for all kinds of potential. So shouldn't get confused with this. See, point number one: gravitational potential potential is not absolute. What does it mean by this statement? Gravitational potential is not absolute. The idea is that we need to predefine, we need to predefine a reference first, a reference first where we assume that gravitational potential is zero. In this case, we usually assume, with the assumption we make, we take the reference point as infinity. Therefore, therefore, we assume we assume that gravitational potential gravitational potential at infinity at infinity is zero. This is the assumption we make. Gravitational potential at infinity is zero. Now, how do we calculate the gravitational potential at a particular point from this assumption? That's pretty simple. Uh, so, we see the mathematical expression in general. This is the way we do it. Uh, Expression, the general expression, use a different color. Using this idea, we can have a general expression for gravitational potential. Gravitation, gravitational potential at a point P is obtained by calculating or evaluating the work done in moving 1 kilogram coin mass from infinity to P along any path, irrespective of the path, any path. The reason is that the gravitational field is a conservative field. Any path, whatever the path you choose, it is irrelevant. So we usually choose, what you may call that, usually choose a straight line. Let's take it. We want to find out the gravitational potential at this point. So assume that this is the point P. We need to work out the gravitational potential. So you bring a body of mass 1 kilogram from infinity all the way to the point P. All right? It's irrelevant with the path you take. You can choose any path, and but it should be brought from infinity. Theoretically, that is the way it works out. So we are taking the body from infinity. Now, At infinity, we assume that here the gravitational potential of any body, any point at infinity, gravitational potential, oh, I find it difficult to write first. We can write gravitational potential at infinity is equal to zero. This is the assumption we have made. So we take a assume that we take a point mass, or we can take any mass that is relevant. We take a point mass. Uh, this is 1 kilogram mass. It's okay. 1 kilogram. So this is a standard mass. Now you take it from infinity all the way to the point P. So the work done can be work done. The expression becomes, this is a little tricky for the first time, is work done. If you calculate, look at here, because the gravitational potential, the expression becomes W. Oh, we use the standard equation, not necessary. W is equals to minus integral the point from infinity to the point P G dr. This is the expression, this is the integral expression we use to work out the gravitational potential at a point in general. This is the standard integral expression from infinity to the point. Sorry, this is the integral expression we use. I put a different colors or not too intrusive. Oh dear. So the general expression is gravitational potential. The integral expression is. So I'll write this equation one more time so you will keep it in your mind. The general expression for gravitational potential. So this is equal to gravitational potential. This is gravitational potential. So any kind of equations, we have this expression. Potential general expression is that field strength integral to the general expression, in specific cases it may differ, minus integral infinity to the point P. We are considering field times dr. This is the general expression for potential and field. How that the second relationship, I was happy about it. That's real matter. There's another expression that connect potential and field. You can write. How do we write it? We are not okay. You can write field. This is the differential expression. Is equals to minus d potential over dr. I don't know whether you have seen this already in case of electricity. Uh, I don't know whether you remember these expressions. No, I'll just put in another box for your comparison. In case of electric field, just for a just for the fun of it. For example, probably you're familiar with these equations. I'm not sure. For example, in case of electric fields, case of electric field, the potential electric potential V is equal to, two equations are there. V is equals to minus integral infinity to R E dr. E is the electric field, or we have the expression E is equals to negative dV by dr. I don't know whether you have seen these equations. I just thought of showing you these equations because they are very similar to what we are doing in here. So the expression for, so let's not focus on that much. The similar equations you can write here for gravitation. I'll write here for gravitation. You may write similar equation. We can write the equations like phi, that is the gravitational potential, is equals to minus integral, let's say, infinity, that looks funny, uh, infinity to R G dr, or you may write G is equals to minus d phi. This is a differential expression. I don't know whether you're familiar with this or to get familiar with these equations, but that gives you a strong theoretical or mathematical description. Now we have seen the expression for the gravitational potential and the definition. So what is the definition? Work done in moving unit, moving unit mass from infinity to a point without acceleration. That is gravitational potential. So we will do one example here, which is crucial. So I'll use a color here. Gravitational potential due to a point charge. So we're trying to find out. This derivation is not very important, but if you learn this, that would be interesting for you. Gravitational potential due to due to a point, no, due to a, okay, due to a point mass, point, there's not enough space, mass. So we are going to work out the gravitational potential due to a point mass or spherical body, both are same. Why? The spherical body can be considered as a point mass with the mass concentrated at the center of mass. So we will try to get this expression, though this derivation is not very important. So let's have a body in here. Here we have a body. Doesn't matter, the radius does not really play much role in this case. Let's assume that the mass of this body is m. All right. So this is the source. This is actually the source. You can write this as the source which creates the gravitational field source. Now we need to find out the gravitational potential at a point P here. So I'm going to mark a point P in here. Let's assume that this is the point P. We are trying to work out the gravitational potential at this point. Now this point P is at a distance r from the center of the sphere. Of course, r is always measured. In this case, these things are important. R is always measured from the source to the point. So I'll mark it as R. Of course, R is measured in this direction. That is very important. And you must remember the gravitational force will be towards the mass m. Now, By definition, if you want to work out the gravitational potential at field, we need to bring a point mass of 1 kilogram from infinity to this point. All right. So we are going to bring a unit mass from infinity all the way to this point. Let's assume that we have a unit mass here as we slowly move them without acceleration to the point 1 kg. So this is moving slowly. Now this red line R is measured in this direction and it is moving from infinity all the way down here. Sorry, not happy about that. Infinity. All right. So right here, you might find this topic a little bit difficult. I'm not surprised. Okay. Now we can do the whole thing, the force, what do you need? G. We need to know the gravitational field strength at a distance r, any point, okay? Let us assume that gravitational field strength, the expression is equal to G m over r square. We have the expression for the gravitational potential. Gravitational potential, we'll write G before that. Gravitational potential, I have to use some shortcuts here, simple. I made everything a little bit simple without following the standard practices. Gravitational potential phi is equal to minus or negative integral from infinity to the point r, because p is at a point r, g dr. We put the value. This is actually gravitational field strength, usually represented by the letter g. All right. So we can just write phi is equal to negative from infinity to the point P, which is at a distance r from the center of the source. And we have, instead of G, we can write G m over r square dr. Oh, sorry, it doesn't look very nice. Dr. So Gm can be taken outside here. So when you integrate this expression, minus Gm times integrate from infinity to r 1 over r square dr. When you integrate 1 over r square, you will get minus 1 over r, and cancel it, and then you of course we need to have, I forgot about it, because we need to consider the direction. So this is minus gm by, all right, minus gm over r. So you can cancel this, it becomes minus and minus get cancelled, so you will get this as gm times. So when you integrate this expression, what you will get is gm times when you integrate, you get minus 1 upon r minus 1 over r, when the limits are, the lower limit is infinity, and upper limit is r. When you just evaluate this, you will get the expression as minus gm over r. So the expression for the gravitational potential, I'll write it one more time. Gravitational potential due to a point mass is given by phi, which is obviously a function of r, is equal to minus g m over r. And you can see that at infinity the value will be 0. So this is the expression. The negative sign indicates that uh, it's a bound state. So the negative potentials generally indicate. What does it mean by negative attractive force? Negative sign indicates that gravitational force is attractive. Attractive forces will generally, so this will generate bound state, generally bound states. You don't need to worry about that. Maybe if there is an opportunity, I'll talk about bound states. So this is the expression we have got. Okay. So this is the simple derivation. You don't require the derivation. You need to remember this expression for gravitational potential, and you need to remember the meaning of gravitational potential. Gravitational potential is the work done in moving unit mass from infinity to a point. Now look at here, because the gravitation is an attractive force to bring a body from infinity to a particular point. You don't need to perform any work. It'll come by itself. So you will get some energy out of it. That's why it becomes negative. So that's it.